Okay, welcome back. Now the demo I'm going to do is called Conservation of Angular Momentum, and this is an actual experiment that we perform in the class. Basically, I have this disk right here, and then I have a ring sitting on the disk. I've shown you this demonstration before when I showed you how to calculate the moments of inertia of different shapes. So it's the same equipment that we use for that, but this could also be used to demonstrate the principle of the conservation of angular momentum. So I'm going to get this disk going at a certain speed, and I have a card here that I've taped, and then when the card goes through this digital timer reads how many seconds the card blocks it, right? So then from if I divide the width of the card by the seconds that it shows, I can calculate the velocity of the tip of the rotating disc, right? The tangential velocity of the tip. So the width of the card I measured it, was 5.4 centimeters. So it's a 0.054 meters. When I want to start it, as it's rotating like this, when the card is kind of in this position, I'm going to turn on the instrument. So it's going to go through it once, right? After it goes through it once, I'm going to take off the ring that's sitting there. So when I take off the ring that's sitting there, what should happen? I have reduced the rotational moment of inertia of the object, so it should speed up. It should speed up at such a rate that the angular momentum of the object is conserved. So the next time it goes through the digital timer, it should go through it quicker, right? So the initial velocity, the tangential velocity of the tip of the object, right? The object looks like this. Then we have the card like that, right? So when it's going through the digital timer, V tangential initial is the width of the card, width divided by T initial. Then when it goes through it again, it's going to record the second time. V tangential final is going to be the width divided by T final. So the V tangential should go up when I take out the ring, right? Then, in order to calculate the angular velocity of the rotating angular velocity, omega initial should be equal to V tangential initial divided by the radius of the disk, right? The radius of the disk. So I divide that, that gives me the initial rotational velocity of the disk, right? And then omega final is equal to V tangential final over R, okay? Once I calculate omega initial and omega final, I can calculate the initial angular momentum, I initial, omega initial. And then I can calculate the final angular momentum, I final, omega final. And I can show that these two are equal to each other, or at least the angular momentum final maybe is a tad bit smaller than the initial angular momentum, but not that much smaller, okay? So let's get it going here. After trying it a couple of times, what I noticed was by my process of me taking out the ring, I'm actually slowing down the disk. So instead of speeding up, which theoretically should, by me taking it out, I'm interacting with the system, and actually the disk is slowing down instead of speeding up. So what I can do is run the experiment backwards. Whenever you stumble upon a dead end in an experiment, you can always devise a different experiment, or you can say, let me run the experiment backwards. These are the kinds of things as a scientist that you should be able to do. You should always be able to be flexible. I can run the experiment backwards. I can actually get the disk rotated, right, without the ring. Then when I put the disk on it, it should slow down. The opposite should happen, right? So then let me I already took out the ring. Let me get this going. Okay, ready? Okay, so you see, very obviously it's slowed down. So there's probably two reasons that it's slowing down as I'm putting it in, right? One, due to the natural effect, I'm adding the moment of inertia of the object. But also because I'm interacting with it, I'm actually slowing it down. So there's a bit of error due to my interaction with the system, okay? So let's see how much of the angular momentum is conserved if the final angular momentum is somewhat close to the initial angular momentum or maybe smaller than it, then I would be happy with the results. So let's see what we get. Okay, so the initial time came out to be 0.0885. T initial 0.0885 seconds. Okay, and then to read the next time, we go like this. You get 0.4063, which is the total time. The way that this instrument gives you it, when you go through it multiple times, it gives you the total of all the accumulated time. So the total time is 0.4063. So if I want to calculate the time, the T final that it took on its next time after I put the ring, T final is going to be this time minus this time. Let's go through our calculations, okay? So I'm going to take the width, which is 0.054, divide a bit, right? Then the angular velocity is also going to drop this, by the same amount. We need to divide the tangential velocity of the tip divided by the radius of the disc, right? So the radius of the disc I've already measured, and that one was equal to 11.4 centimeters. 11.4 centimeters, which is 0.114 meters. The mass of the disc we're going to eventually need, that's going to be 1.43 kilogram. 1.43 kilogram rads per second. Okay, so the initial angular momentum of the disc, remember I had the disc originally, right? So that's equal to 1/2 the mass of the disc, the radius of the disc squared, times omega initial. So 1/2 the mass of the disc is going to be 0.0497. That's going to be units of what? The units of moment of inertia is kilogram meter squared, and the units of omega is radians per second. So this is going to be kilogram meter squared per second. Okay? So the final angular momentum is going to be what? Well, it's going to be the original moment of inertia, which is this thing. Then on top of that, I'm adding the ring, right? So I need the mass of the ring. So the mass of the ring I've already measured. Mass of the ring is 1.42 kilograms. So very similar to the mass of the disc, 1.42. Okay, 1.42. Now the ring has an inner radius and an outer radius. The thickness of the ring is 1 centimeter. So the inner radius is smaller than the outer radius by 1 centimeter. The inner radius is 5.4 centimeters, R1, 0.054 meters. The outer radius is 0.064 meters. Of the mass of the ring, which is 1.42, and then the inner radius, 0.054 squared, plus the outer radius, 0.064 squared. Right, so this gives you the total moment of inertia, okay, of the original moment of inertia of just the disc, plus the moment of inertia of a ring. 1/2 the mass of the ring, inner radius squared plus outer radius squared. So then we take this moment of inertia and we multiply it by the L final is going to be I final, omega final. And my omega final was 1.49 rads per second. Okay? Okay? So is the angular momentum conserved? Not really, right? So even though in theory, angular momentum is conserved, in other words, when I put something on, I'm adding the rotational inertia, it should decrease. But since I interacted with it, so the angular momentum probably dropped. So this number is supposed to be close to this, but a bit smaller. But it actually came out to be a lot smaller. So we can say, what is the percent loss of angular momentum? Okay. Now, what's going to happen to the kinetic energy, the rotational kinetic energy of the system? In this case, because I put the object on it slowed down, the kinetic energy is going to decrease, right? So you multiply here 1/2. What was the I initial? 929 kilogram meter squared. So the initial moment of inertia, 0.00929, right? Omega initial is equal to, and then the omega final was equal to, omega final was equal to 1.49 radians per second. So then I'm going to do 1/2 I initial, omega initial squared. So that's initial kinetic energy system. And then the final kinetic energy of the system is going to be 0.5 times the final moment of inertia of the system, 0.0 0.1427 times the final angular velocity, which was 1.49 squared. So this is going to be here. So even if the total angular momentum of the system had been conserved, but because this is similar to an inelastic collision, the kinetic energy will always drop down by a huge amount. Very similar to a totally inelastic collision when two objects come and collide with each other and stick together. Right? So then the percent loss of kinetic energy is going to be... Okay, now let's do something similar. Now I'm going to have the ball here, but now I'm going to go in the opposite direction. I'm going to tape the ball to the side of the object. Okay, right, so the ball is kind of going to be on the verge of wanting to slide out. So I'm going to get it going. This one I'm going to go in the opposite order. I have the ball initially there, then I'm going to cut the tape with scissors and the ball is going to fly off, right? When the ball flies off, it should start speeding up. So I'm going in the opposite order, whereas the other one, it was easier for me to place the ring on the top. Now it's easier for me to, instead of placing the ball, place the ball initially, then cut it with a scissor and see what's going to happen to the angular velocity and the angular momentum, right? So let's reset this timer. So the mass of the ball is going to be... The other thing that's important is the distance from the center of the disc to the center of the ball. Okay, now I'm going to have to use the parallel axis theorem to find out the moment of inertia of the ball. So the ball is sitting so that its edge is kind of flat with the edge of the disc, right, like here. So the center of the ball, distance from the center, it looks like this now, kind of coinciding with the edge of the disc. So the distance from the center of the ball to the center of the disc, that's going to be the difference between the radius of the disc, 0.114, minus the radius of the ball. And so if we subtract that, so we get here 0.089 meters. Okay, now let's get this spinning. Spinning here. So the initial time was 0.1503. The initial 0.1503. Okay, so the final time was 0.2688. So that's the total time, right? Then you subtract the initial time from that, that gives you T final. So the initial time 0.1503, that gives you 581.1185. So now we can calculate the V tangential, V initial tangential, the width, which was the width of the card, 0.054 divided by the initial time, 0.1503. Moment of inertia is just going to be the disc by itself because I cut the ball, right? The ball left, so it's going to be the disc, so that's going to be 0.00929 times omega final, so that's going to be 3.85, right? So that's going to be equal to the sum of 0.00929. Then I'm going to have to add the moment of inertia of a sphere, right? What is the moment of inertia of a sphere? It's the 2/5 of the mass of the sphere times the radius of the sphere squared, right? 2/5 the mass of the sphere. The mass of the sphere was 0.5 kilogram. The radius of the sphere was 2.5 centimeters, right? So 0.025 squared plus, then you shift the moment of inertia of the sphere from here to here using the parallel axis theorem, right? So then you just say here, the mass of the sphere, 0.5 kilogram, times the shift amount, which is 0.089 squared, times you multiply that by the initial angular velocity, 3.15. Okay, so what is the initial moment of inertia? So you're going to add to this all this stuff. So 2, 1. So notice the angular momentum was lost again. By me even cutting it, I'm kind of vibrating the system, and then it's taking a while for the sphere to roll off, right? And as it's rolling off, it's probably slowing the system down. So angular momentum is not conserved that much, but it is a bit better than the previous result. So it also shows that the final angular momentum is smaller than the initial angular momentum, but not by that much. So you can kind of see the idea of angular momentum conservation to hold true. So that is pretty reasonable, because that by just cutting it and interacting with it, you can cause the angular momentum to go down by that much, right? How about the kinetic energy? Should it increase or decrease now? So when the ball is going out, right, the velocity is increasing, and since kinetic energy is proportional to velocity squared, this time you actually gain kinetic energy, right? This is basically opposite of an inelastic collision, right? It's the inelastic collision run backwards in time. So imagine if the ball was coming from the side and landed on the disc, right? That would be an inelastic collision. So if the ball landed on the disc, it would slow the spin rate of the disc, right? So me putting the ring or the ball coming and landing on the disc, those are all cases where it's like an inelastic collision where the kinetic energy of the system decreases, right? Me taking the ring out and the ball going flying away from this, that's an inelastic collision run backwards in time. So the kinetic energy of the system is gained this time, right? So we can always run these backwards and forwards, and one of them you will gain energy, one of them you will lose energy. This one you're actually gaining kinetic energy, right? So the initial kinetic energy, so you see you are actually gaining kinetic energy. So the percent gain in kinetic energy, where's that energy going? It's going in the flinging the ball outward, right? So now the energy, the ball has a kinetic energy as it's being flung out, right? And then eventually it goes and hits the ground, and then that energy goes into potential energy, right? And then converts back into kinetic energy when it hits the ground. So it's just basically one form of energy goes to another, and then eventually it makes a sound, so it goes into sound energy, and so on and so forth, right? So you can see here a good two examples of inelastic collisions, where one inelastic collision run forwards in time, one run backwards in time. We have shown that in both instances the angular momentum of the system is lost a bit by me interacting with the system, but it's not lost that much. Particularly in the second case, we got a much better result, right? But the kinetic energy in one case is lost big time, and in the other case it is actually gained, okay? So this is a good example of conservation of angular momentum applied to different kinds of situations. Thank you very much.